Alright, I better end that there. I don't hold the copyright to that song or have permission, so I'm just going to call that fair use and cut it off there. That song is I Got the Power by Snap. So we are going to talk about power today. Power, as you should remember from last year's classes, whenever you took Physics 1, is the rate at which work is done or energy is converted. I mean, that's what work is. When you're doing work, you're transferring energy from one system to another. Well, the same thing here. When you are transferring energy from electrical potential energy and turning it into some other form, we want to calculate how long it takes for a certain amount of energy to be transformed in that way, or what we want is the rate at which that energy is transferred. So what we want is to calculate the power. But we have different quantities than we had last year when we were talking about work, and we calculated the formulas for power last year with using the concept of work. Here we're going to use those quantities that we know about, and we're going to look at a very simple circuit, this representative circuit here, if you will. And in this circuit, there is a potential difference of V from this point in the circuit, the positive plate of my battery, through the resistor down to the negative plate of my battery. And so charges move from here through here, and energy is transferred. Now, it's exactly how the energy is transferred is an interesting thing. It's a lot of time on the internet has been spent recently with people arguing about how energy is transferred through circuits. We know that although the charges themselves flow through the circuit inside the wires, the energy is actually transferred outside the wires. And it's interesting at how that's done. We're going to learn a little bit more about that when we learn about magnetism. But I will also going to post on the Canvas, I'm going to post a couple of links to some interesting little videos if you want to watch them. They're completely voluntary. It's nothing about what we're doing for the AP test or anything. But anyway, energy is being transferred from potential energy here into some other kind of energy in that resistor, be it heat, energy, or the resistor stands for everything that's useful in the circuit that it's doing for us, like providing light or whatever it is. Well, in order to talk about how much energy is being transferred per second, let's get how much energy is being transferred per coulomb of charge that flows through my circuit. We already have a name for that. That's the potential. The potential is the name we gave to the amount of potential energy that per coulomb of charge that flows through your circuit. So 1 volt means 1 joule of potential energy is converted to something else per coulomb of charge that flows through that circuit. Well, that's not quite what we want, though. We want the rate over time. But we have another concept that we can use, and that's the current. The current is the rate at which the charge flows over time. So the current is how many coulombs of charge flow through your circuit per second. And so, you know, the definition of current would be the amount of charge per unit of time. Well, if you want to get the amount of energy conversion per unit of time then, what we can do is we can take the voltage, which is the energy change, the energy that gets converted to some other kind of form of energy per coulomb of charge, and multiply that by how many coulombs of charge flow per second. And that should give us the energy change per second, which would be the power. Well, that means that we're going to take this first thing here, that's the potential difference. That's the voltage times the current. Oh man, that's big for us there. And that gives us voltage times current gives us the power. So our formula for power let me make this a bit smaller. Our formula for power is potential difference or voltage times the current. And that is one of the formulas we're going to use this formula. It's one of the formulas we're going to use for this power. But since we know how these are already related to each other, voltage and current are related to each other in the definition of resistance, if we can also use the resistance in our formula, then we can write it two different ways. For example, we know from the definition of resistance that it's equal to the potential difference across the circuit divided by the current flowing in that circuit. So therefore, the current is equal to the voltage divided by the resistance. And so the power must equal the voltage divided by the resistance, that's the current, times the voltage, which gives us the voltage squared divided by the resistance. And then we can also say, since voltage is equal to I times R, the power must equal I times R, which gives us the power is equal to I squared times R. Now, both these formulas are equivalent to that. They are used somewhat differently, though. This one is very often useful when doing an analysis of a circuit. When we know what the resistance is in a certain branch of the circuit, or if you know what the voltage across the circuit is. Like, say, for example, they say that you have a household and all the circuits are in parallel and they're 120 volts. Well, then we know what the voltage is. And so the bigger the resistance is for a constant voltage, the smaller the power is going to be. So if you want to have a high-powered device, you want it to have a small resistance. In that context, where the voltage is a constant. But very often it is the case that sometimes you want to talk about the power that is wasted, if you will. There's resistance in your wires, or there's resistance somewhere in your circuit that you don't even want to have. It doesn't do anything good for you. And very often the formula they use for that then, when they're talking about those losses, they'll use this version of the formula for power. They even call it I squared R losses, meaning how much energy is lost per second because of those resistances that you want to eliminate. I'm talking here about the resistances in the wires that are carrying the electrical current from, where it's being produced, where the electrical, the generator is, to where it's being used. The smaller you can make the resistance, the better. But there's a certain limit to how small you can make that resistance. So then you want to make your current as small as possible. And it turns out you can make currents really, really, really small on those power transmission lines, for example, if you make the voltage really, really, really big on those power transmission lines. And we will talk a little bit more about how that's done when we talk about magnetism in the spring semester, or when you talk about magnetism in the spring semester. But that's usually that's very often where that formula is used, okay? And talking about resistive losses in a circuit. But all three of these formulas are useful. This would be a good time maybe to review some of the other formulas that we've done so far in this electrical unit. So let's look at some of the other ones we've done. We started off with the definition of current. The amount of charge per unit time. So that is one that you seem to memorize. I'm going to here give some idea for whether you need to memorize a particular formula or if it's something that you can just look up on the formula chart. That's one you need to memorize. And then the formula for the current and how it relates to the drift velocity. This is one that you need to kind of understand conceptually. You don't have to memorize it though, although it's not that hard to memorize because we have kind of called it the Nevada formula. That's kind of a mnemonic. It's good to understand there is a relationship between the drift velocity and the current, and also between the cross-sectional area and the current, so forth. But you can look it up. And then there's the definition of resistance, sometimes called Ohm's law, but we know Ohm's law means that definition of resistance and that it's a constant. The voltage is proportional to the current, so R is a constant. That's one you just need to know. We use it all the time, so memorize that one. And then there was this formula for the resistance and how related microscopically to the resistivity. That's one. You don't necessarily have to memorize it per se, but really you have to understand the proportionalities involved, so you're kind of memorizing it as it is. In other words, if you are given a question about a conductor, and they say the conductor's length is doubled, but everything else is the same, what's going to be the resistance? Well, you should know that it's proportional to the length, and also the resistance is inversely proportional to the cross-sectional area, and that it's directly proportional to this constant that has to do with the material. It's a constant for a given material at a given temperature, and so forth. So I say you don't have to memorize it. I say you can just look it up, but if you understand those proportionalities, you kind of already have it memorized anyway. So there you go. And then there's the formulas we just learned just now. Power, we have 3 formulas for that. Boy, things are going crazy on my whiteboards today. There we go. The power is equal to the voltage of the current, and then with the resistance is known, we have various ways of expressing that same relationship. And then there's this one. And I say, on this one, you definitely need to know that power is equal to voltage times current, and then the other two you can quickly derive if you need them, I suppose. Just the relationship that gives us the voltage drop across a battery. It's really, I say derived, but you kind of know it already. If you just understand that a battery consists of a pure battery voltage, the EMF, that's the voltage that the battery puts out because of the chemical process it has in it. And then from that voltage you subtract the voltage drop caused by the internal resistance of the battery itself. So we use a small r for that. So really this is the terminal voltage of the battery, the potential difference between the one terminal and the other of the battery. That's equal to the EMF minus whatever voltage is dropped inside of the battery because of those internal resistances. I say derive it, but it's really something that should be fairly clear to us from the experiments that we've done. Okay, let me see if I can get it to go forward one more. Okay. There we go. All right. So I have some questions for you to answer. They're in a little quiz, just a short little quiz. It's just the questions that are embedded in this PowerPoint, but I'm giving you a chance to do them in the form of a quiz. And once you finish those, any further assignments I will make sure get put after the quiz on Canvas. So good luck.